we've been doing so far, and I'm going to try not to scream in the video since I was told that I was screaming on the last video that I did. So I'll try to talk in a normal tone of voice and not scream. But since we do have some folks absent, it might be easier for them to have a video. So what we've been doing so far is we've been doing ideas where you're going to pick this or this. The clue word, the key word that we've been using has been or. Today we're going to talk about what happens if you do and. And so we're going to be talking about actually picking multiple things. Like what if I pick a red marble and then I go back in the jar and pick a blue marble? Like what's the probability of doing two things? Picking two cards out of the deck. So we're going to start talking today about the word and, which is going to bring us to a multiplication rule. Now there's two parts to it. That's why you have two sheets. Okay, here's the first part. If the events are independent, if what happens the first time has no effect whatsoever on what happens the second time, then those two events are considered to be independent. For example, if you take a coin out of your pocket and you toss it, and the first time you get a heads, you pick the same coin up and you toss it again. Just because you tossed a heads the first time, does that mean anything about the second toss? No. Coin is still the same. There's an equal likelihood that you still have the same odds the second time, right? Okay, now contrast that to this. What if I have a certain number of marbles in a jar? Okay, let's say I have 10 marbles in a jar. I reach in and there's a certain probability that I'm going to pull out one particular marble in the jar. What if I keep that marble? Say I'm going to keep this marble, so I'm not going to put it back in the jar. Now, when you reach in, has that changed the odds of what you could potentially draw the second time? Yes, because now there's fewer marbles to choose from. So what that means is what happened in the first instance does affect the second instance. Does that make sense? So today we're going to talk about independent events versus non-independent events, things that do depend on each other. We're going to talk about the multiplications and rules for probability where we're independent. If you land on heads after tossing a coin and you're going to roll a dice or a die, those two things don't depend on each other. Okay? So here's the real quick and easy way to think about finding the probability. To find the probability of two independent events, like rolling a dice, tossing a coin, find the probability of each event occurring separately and multiply the probabilities. You will want your calculator. You will reduce these fractions. These numbers can get very big. You might want to use your math fraction key to reduce it, or you can use you can reduce the fractions before you multiply. So get your calculators ready to go. Okay, so we just spent some time talking about union and intersection. So this is what it looks like. The probability of A and B, because today the word is and, is the probability that A will happen multiplied by the probability that B will happen. Or this would be the way it would be written with notation. Okay, I used to always teach it with the word and, but on the exam, they're going to start to show you the union. Okay, so when you see union, you know that means bring the things together. That's like and. So the probability of A union B, two things happening together, is probability of A times the probability of B. So I'm trying to update what I've used before to make sure that you at least know what the probability looks like. Just jump right in and do one. A dresser drawer contains one pair of socks with the following colors: blue, brown, red, white, and black. Each pair is folded together in a matching set. Aren't your drawers really organized with your socks? How many of you have well-organized drawers of socks? Oh my God, you are all alone. Wesley has a nice drawer of socks at home, probably organized by color. Okay. What is the probability of picking red socks the first time? What's the probability of picking red socks the first time? Remember, it has one pair of each. One blue, one brown, one red, one white, one black. He has one chance out of what? 5. If you replace the socks, ding, 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 important. You're going to replace the socks. You just reach in the drawer because, you know, you're kind of sleepy in the morning. Oh, it's just, oh, man, I didn't want the brown ones today. Put them back, reach in the drawer again, pull them out again. Does everybody understand what we're talking about? Replace the socks. What is the chance of picking red socks a second time? 1 out of 5. Because you replace the socks, now the two events are considered independent. You know, because I replaced it, it's still the chances are back. It says, overall, what is the chance of picking red socks both times? Okay, it would be probability of red and another red. So you do each one independently. 1/5 for the first time times 1/5 the second time. The chances of getting red both times becomes what? 1 out of 25. You multiply the numerator, you multiply the denominator. Everybody good with that one? Are we good? A coin is tossed and a single six-sided die is rolled. What is the probability of head side on a coin? 1 out of 2. What's the probability of rolling a 3 on the die? 1 out of 6. What's the probability of landing on the head side and rolling a 3? Notice the word is and. It would be 1 out of 2 times 1 out of 6, which would be 1 out of 12. I have 1 chance out of 12 of getting both of those events to happen like I want it to. So far, so good? Okay, number 3, a card is chosen at random from a deck of 52 cards. It is replaced. Ding, 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 ding. That's key. And a second card is chosen. What is the probability of choosing a jack and replacing it and getting a 8? What's the probability of doing a jack? You got 4 out of 52. I strongly suggest before you multiply that you might want to reduce that first. Otherwise, you're going to be dealing with some really large numbers. So I'd probably reduce that to what? 1/13, okay, times the probability that you're going to get a what? 8. What's the probability you're going to get 8? Still 4 out of 52, or what? 1/13. Want to multiply together. What's your chances of getting a jack and an 8? 1 out of 13 squared is 169. Do you understand what we're doing? Pretty easy, isn't it? You want to give number 4 a try? I'm going to pause, let you do number 4. Did anybody count yet and tell me how many total marbles we have in the jar? 16 total marbles. So we want a probability of a green. So we have how many greens? So do the probability of a green, which would be 5 green ones out of 16 total, times, what about yellow? 6 of the 16. Now, you can multiply numerators and denominators, and your calculator can reduce it, or you might want to reduce it first. It's up to you. You do have a calculator which can do, and I would get 30 on the numerator, and what's 16 squared? 256? All right, now, the thing of it is, if I do 30 divided 256, math key, fraction, enter, enter, it does reduce it for me to 15 over 128. Is that what you guys got? So make sure that you take it all the way out. So I would have 30 over 256, which reduces to 15 over 128. Final answer. You would be expected to reduce it. Okay, so grab your calculator if you need to. Use it to let it do the work. Okay, 5. A survey found that 9 out of 10 students like pizza. 3 students were chosen at random with replacement. Ding, 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 ding. What is the probability the first student likes pizza? 9/10. Okay. So probability the second student likes pizza? 9 out of 10. What's the probability the third student likes pizza? 9 out of 10. What's the probability that all 3 students like pizza? 1 and 2 and 3. 9 out of 10. Times what? What's 9 cubed? 9 cubed is 729 out of 1,000. Does that reduce? I don't think it does. A nationwide survey found that 72% of people in the United States like pizza. Convert 72% to a decimal, because we've been doing a lot of fractions, but you are going to see a lot of percents, and percents can be easily changed to decimals. So what is 72% changed to a decimal? 0.72. All right. 3 people are selected at random. What's the probability that all 3 people like pizza? So it's all 3 people. So it'd be like the probability of the first person likes pizza, and then the second person, and then what? The third person. And every time we do an and, we have to do a times. So it'd be like, well, the first person has a 0.72 chance, right? It is. You can do 72 over 100, but then you have to cube it. It would be 0.72 times for the first one times 0.72 times 0.72. What'd y'all get for that? 0.373 is good enough. Everybody good? Yes, Miss Jessup, I am, or no, Miss Jessup, I don't have a clue. All right, we're good. The spinner. Spinner's numbered 1 to 7, and you're going to toss a coin. What's the probability of getting an odd number on the spinner? Spinner's 1 to 7. That's really strange, isn't it? So I have 7 equally shaded parts on the spinner. So how many of those would be odd? Right, 1, 3, 5, and the 7th one. So I have 4 chances out of what? 7 that I'm going to get an odd number. Is everybody right? There's 4 chances out of 7. All right, times. Now the second one has got to be what? Tails. How would you get tails? What's your chances of getting tails? 1 out of 2. And your answer is 4 out of 14th, but it does need to be reduced to 2/7. All right, I'm going to pause and let you see if you can finish from, what, 8 on down to 12. 8 on down to 12. Go. You can pause the video and work 8 to 12 and then check your answers. All right, let's come back together and check our answers to the first, well, it'd be for the first 12, but it would be from 8 to 12. 8, did you guys get 149? No, I'm not going to do that. 149th? Okay, it was probably both balls are chosen are green. It would be what? 7 out of, no, green. 3. Number 8. Did I do number 8? Yeah. There's 21 total, isn't there? So it would be 3 out of 21, or that would be the same thing as what? 1 out of 7, and that would be for the first marble, and then if I put it back, I would have 1/7 chance again to draw a second marble, and when you multiply, you get 1/49. What about number 9? Sam, what'd you get? Yeah. 1 over 21. Good. Number 10. Number 10. Volunteer? I got 10 over something. 147. See, a bunch of you had it because I already saw it. You just didn't want to say it out loud. It's okay. Number 11. You pick 2 days of the week. 149. The Tuesday is 1 day of the 7th, 1 day of the 7th, which is 149th, and the last one. If you have to draw, and that's supposed to be hearts, that is a misprint, supposed to be hearts. Isn't it 13 cards out of the deck of 52 are hearts? Or is that the same thing as what? 1 card out of every 4? So if you do that 4 times, the first card I have a 1 in 4th chance. The second card would also be 1 in 4th. Third card's 1 in 4th, and the 4th card is 1 in 4th. 1 out of 4. Multiply 1 out of 250 6. All right. Now, that's multiplication rule, which is an and, but it's, notice that I use the key term a lot, with replacement, okay? In other words, what happened the first time doesn't have any effect on the second drawing of the marble or the second choosing of something. Okay, now, we've talked about independent, now we're going to talk about dependent, right? This means, given that we just did something the first time, now it is going to have an effect on what I do the second time. Okay, so what happens does have an effect. So we've got an example right here, and I chose to type this in here so that you could have something to look at if I don't say it the right way. So let's say we are not replacing the card. We're playing a game, and I have to reach in the deck and pull out a card, and I have to keep it in my hand. So then I have to reach in the deck and pull out a second card. My odds of getting the cards I might need are going to change because now I don't have as many cards in the deck. So here's the idea. Suppose that we want to, says the probability a card is chosen at random from a deck without replacement, a second card is chosen. What's the probability that you choose a queen the first time and a what? And the second one is a jack. Now, the queen, there's 4 chances out of what? 52. Let's say you successfully accomplish that. I reach in the deck, I get my queen, yay! I'm going to quietly keep that on my hand, keep it in my hand. Now, when I pick the jack, I still have 4 jacks in the deck, but do I have as many cards to pick from? Now there's only what? 51 cards. Do you see how it just had an effect? So it's not going to be 452 times 4 over 52. It's going to be 4. Well, you all can see. 4 chances out of 52 the first time. 4 chances out of 51 the second time, because because I did not replace it, it did make a difference. All right, let's just take a look at some. I do need you to understand the notation, so follow me if you would. This right here, which is right here. Do y'all see that slash mark? Okay, this says the probability that A and B happens is the probability of A multiplied, so we're still doing a multiplication rule. This is like multiplication rule number 2. The probability of B is only considered given that A has happened. Okay, so that means that it may not be what it would be otherwise. So this says probability of A times the probability of B given that A has happened, given that something else happened before. And that's where we qualify. All right, let's do number 13. Mr. Parietti says needs 2 students to help him with a science demonstration in a class of 18 girls and 12 boys. He randomly chooses one student who comes to the front of the room. He's going to choose a second student from those that are still seated. What's the probability that both students that are chosen are girls? I'm going to imagine choosing making my first choice and my what? Second choice. What's my probability, what's my odds of getting a girl the first time? Because this is what the probability of getting a girl and getting a second girl. 18 chances, 18 girls out of 30, which that can be reduced. And then how about the second time? If I successfully got a girl to come to the front, now she's not in the mix. So I only have 17 girls left, and now how many girls, or how many total people are there? 29. I would probably reduce that first, but let your calculator do the talking for you. Multiply the numerators, multiply the denominators. These are going to give you numbers that get really big. You would definitely want to have a calculator handy. Okay, so if I was doing this one, 18 times 17, did you get 306 for the top number? What's 30 times 29? 870. So now it's 306 divided by 870. I'm going to go straight to my math fraction key, math, which is fraction, enter, enter. My final answer is 51 over 145. Does everybody get what we just did there? Use your calculators. In a shipment of 20 computers, 3 are defective. We don't know which ones they are. 3 computers are randomly selected and tested. What is the probability that all 3 are defective if the first and second ones are not replaced after being tested? Which means I got a computer out of the 20, and I took it, and lo and behold, when I tested it, it was infected. Wow. Then I go back, and I get a second computer at random, and I go test it, and guess what? It is infected too. What's the probability that I'm going to get all 3 defective computers if I click 3? You got it figured out? First, second, and third. Write it out. What's my chances the first time? I got 3 computers out of 20. What about the second time? If I successfully got a defective one, how many's left? There are only 2 left that are defective, and now there's only how many computers left? 19. This is what we mean by the odds of B happening given that A has occurred. Okay? Given that we did choose a defective one, now what does my odds change to? What about the third time? There's only 1 left out of all 18. The odds of you getting all 3 defective computers is going to be amazingly small. And where's my answer key when I need it? Had it a minute ago. Da-da-da-dum. Yeah, here we go. And the winner is? You might get 6 out of 6,840, but reduces to almost, 1 in 1,000. That's, your odds of doing that are incredibly small. Okay, 4 cards are chosen at random. 4 cards. What is the probability of choosing a 10, then a 9, then an 8, then a 7? Does everybody understand? Okay, so I'm going to choose 4 cards. Okay, this is my first pick, my second pick, my third pick, and my fourth pick. Okay, first time I want to choose a 10. How many 10s are in the deck? There's 4 10s out of 52. Now, given that I successfully got the 10, and I'm keeping it, I'm holding that card, how many 9s are there remaining in the deck, and how many cards remain in the deck? There's still 4 9s left, because I want a 9 the second time. Does everybody get it? So that number doesn't change to 3. It's still a 4, because there's still 4 9s. But there's only what? 51 cards. See, up here, my top number changed, and my bottom number changed. Okay, here my top number is not changing because it's a different scenario. What about the third one? How about an 8? How many 8s? 4 8s, but now there's only what? 50 cards remaining. And then a 7, there are 4 7s, but there are only what? 49. These numbers get really big, and I have a really big bottom number. I got millions when I just multiplied it straight out. It reduces. Anybody got it reduced yet? I think I got a 32 on top. Did anybody else get that? I think I'd reduce that one by hand. Does that one reduce? This one can't, the math fraction key doesn't work on it. It's so big, the math fraction key is like, oh, I give up. You have to do it by hand. Did you get 200? It's actually better if you do what? If you reduce these first, otherwise you don't have to reduce the huge numbers. I ended up with 256 out of like 6,497,400. Anybody get something like that? Now, do we know 2 goes into those? Yes. Could you reduce them by half? Yeah. Could you probably 4 goes into them? It would be harder to do this by hand. It might be easier to come back here and say, you know what? I do know 4 out of 52 is the same as what? 1 out of 13. And maybe reduce my numbers to where my calculator can handle it. I know 4/50ths, that can reduce. I think I can do that in my head. What does 4 out of 50 reduce to? 2 out of what? 25. Now, if I multiply those new fractions, I think my calculator can probably handle it. Why don't you try it? Well, So number 15 is giving me great big numbers. We're going to reduce the fraction. So 1 times 4 times 2 times 4. I got 32, and then I have 13 times 51 times 25 in the denominator times 49. I got 32 over, I don't know that that reduces, 32 divided by 812,175. Math key, fraction, enter, I don't think it reduces. It doesn't. It doesn't, the math doesn't reduce. So I got 32 over 812,175. The numbers get really, really big. All right, we do know that the multiplication can get really big numbers. Let's just make sure in these last few examples that you know how to set them up. You tell me what to write. How many cards am I picking in number 16? 3 cards. So I'm going to leave a space for my first choice, my second choice, and my what? Third choice. What's the odds of getting an ace? And it says 3 aces. That's like pulling 3 aces in a row. What's the odds of doing that? How many aces are there available the first time? 4 out of 52, which I might reduce that on my paper to what? Is that the same as 1 out of 13? Okay. Now how many aces remain? 3. How many cards are there left? 51. And then if I successfully get an ace the second time, what's the odds of getting it again? How many aces are left? If I get 1, then I get 2. Isn't there 2 left? Oh, okay. You mean 2 out of 50, which is 1 out of 25. You're a little bit ahead of me. You are correct. 1 chance out of 25. So 3 out of... That does reduce, doesn't it? I got 1 out of something. Huh? That does reduce. Is it 1/17? I got 1 out of, is it 5,000 something? 5,525. Okay, I'm going to stop. All right, I'm going to post the answers to 17, 18, and 19, and you guys will do the back. On the back, let me remind you, could be a basic probability, could be addition rule, or multiplication rule number 1, which is with replacement, or multiplication rule number 2, which is without replacement. So the back is mixed. So just know that it's not any one type. It's just, it could be a variety. It's kind of like mixing them up to make sure that you know how to do all of them. All right, these would be the answers then to the last 6. So if you paused and you worked them out, you can always check. But guys, you need to complete the back. There are 14 on the back, and they're mixed. There may be some add rules, basic probability, multiply rules, both types, with replacement, without replacement. Read carefully.